All right, so today we're going to do something fun. We are going to make a network utilization, a little bandwidth monitor type program for Linux in Bash. We're going to use nothing but Bash built-ins. It's going to be on the terminal and it's going to look really cool. If you've ever wanted to build one of these like visualization tools before, or you wanted to learn more about the proc file system on Linux, we're going to dive into that in this video. So yeah, it's going to be a lot of fun. Now, technically this is a follow-up video, or you can think of it as like a part 2. For the first video, we made a CPU utilization tool in Bash. It's really cool. You can go check it out. We're going to build on that. In fact, the first part of this video, I'm actually going to spend making a couple changes to the CPU tool because we're going to borrow a little bit of that logic for this network visualization tool. And I'm sort of starting a mini series here where I'm making resource monitors in Bash. We have the CPU one. We're going to build the network one today. Maybe we'll do like disk utilization next. I don't know. You guys let me know in the comments, but you want to see. But yeah, don't worry. If you haven't seen the part 1, go check it out. Obviously, it's a fun video. I think it's a fun watch. But if you haven't seen it, don't worry. I'm going to go over some of the code here. We're going to get that out of the way. I'm going to go over what we built in the last episode, and we're going to go forward and build something really cool and new in this episode. So yeah, this is going to be a ton of fun. Let's jump in. All right, now before I jump in and make the new tool, what I want to do is I want to show the old tool and I want to do some bug fixes and make some small changes to it based on your comments on the video, based on some GitHub issues I've received. You guys have given me some great feedback, so it's awesome. So I want to start the video with that, and then I'll jump into creating the new tool. If you're impatient, I'll go ahead and put timestamps below so you guys can jump forward to it. But I promise it'll be fun and interesting because it's me and my content's awesome. So there you go. All right, so here we are. We are logged into my Linux virtual machine. As you can see, we have Linux here. If we run this, we can see that my machine is void.rapture.com. This is Void Linux. We are running Void Linux on this machine. I don't have NeoFetch installed. Could have sworn I did. Yeah, so there we go. There's NeoFetch. Totally was installed the whole time. Shout out Dylan for NeoFetch. I hope the farm is treating you well. But yes, I won't waste any time. Let's show you the tool that we have written from the previous episode. As you can see, we have a script here called CPU. I'm going to go ahead and fire open a tmux here. I've been messing around with tmux a little bit lately. It definitely seems like a cool tool. I've used it more in the past, but here we are. So let's go ahead and let's split this. Let's run up here and let's run this CPU utilization script up here. So you can see this is what it looks like. It shows the percent used of the CPU. I have 4 cores in this machine and they're not really doing much, as you can see. So let's go ahead and simulate some data. We can do while true, do true, done. So this while loop does absolutely nothing, but it will completely destroy 1 core. So there you can see it's been scheduled to CPU 2, and it will stay on that core for a long time. Eventually, the operating system may schedule it to a different CPU. We might be able to see that happen here. Hey, look at that. Wow, speak of the devil, we got moved to CPU 1. So that's pretty cool. That's the operating system scheduler jumping in there. But yeah, that's pretty cool to see. What I didn't show in the previous episode, take a look at this. Let's go ahead and cancel that. We call true here, which is built into the shell. We can prove that with type true. You can see that it's a shell built in. But true also exists on our system. Well, it exists in a lot of places. Apparently I have it in my path all over the place. We have been true. So let's go ahead and rerun that loop. But let's, instead of using the shell built in here, let's actually fork an exec out to the external tool. This is going to be doing a lot of fork and execs. Every one will be scheduled differently, which means, look at this. This is beautiful. You can see that we're kind of going evenly across all the 4 cores. It's a little bit above 25%. That makes perfect sense. So yeah, this is what we built in the previous episode. We'll be going over a little bit of the code here, and I have a couple little changes I want to make to this code. So let's get started with that first. From the last video, I got a lot of comments on this. If we scroll down into this source code, I'm not going to dive too deeply into this. Go watch the first video if you want to see it. But a lot of people had something to say about this code right here. I had guest nice defined here, but I wasn't using it here. So here, I'll just do this, it's easier. I'll highlight it with my mouse. Look at this, guest nice. We weren't using guest nice before. I had duplicated the variable incorrectly. We were getting good enough results, but it was technically wrong. A bunch of the commenters noticed it, but shout out to T73Biz over here for actually opening an issue, and you can see that they show what the old code was, where I used a nice here when I should have been using guest nice. So I went through, made this change based on this, and committed this. So this code that you're looking at already has that fix in there. So that's a simple bug fix that was committed from last episode. All right, now beyond that, there was another bug that you may have noticed, which was unfortunate that it's there because the bug doesn't actually exist on GitHub, at least with the latest commit. But if you notice that the CPU seems to grow over here, you can see the percent sign is right there. If I close this out, you can see that now we get this double percent sign. It's not clearing this area over here. In the latest GitHub branch, this is not the case. This is because I was doing some local development work, so I'm sorry this bug showed up here, and it kind of stole some of my thunder because I was going to artificially create this bug and then we can solve it together. But we're going to solve this bug. But just to let you know that on the latest version on GitHub, as I'm recording this video, this bug didn't exist. I introduced it as part of the behind the scenes work here. But because we hit it, I'm going to show you the behind the scenes magic, so don't worry about that. So one of the things here from this code is that because we built it from the top down, we did some sort of things that can be optimized out. So for example, we clear the whole screen. We clear the whole screen, we move the cursor to the top position, and then we print all of the output. And clearing the whole screen is fine, but we don't need to do that. We could actually just move the cursor to the top and then overwrite what was there. So if we do that, if we don't clear the whole screen, we actually can save some frames and we can make it run a little bit faster, but that's what created that % multiplication problem that we saw happening. So we have to now deal with that, unfortunately. But I promise this is worth it, and we're gonna go deal with that problem really quick. So as you can see right here from last time, we have this logic that says state equals color3, then the % with the actual literal % and then the reset character. So we don't do any padding here. We would need to pad this. So let's go ahead and pad that. We can do that very easily using printf. Actually, I'll show you guys right here. We can printf a %s here, and then we could put whatever we want here. Let's say 57.0%. This is just a string, nothing special. It'll just print 57.0% there. Let's put a new line here just so we can visualize it easier so the prompt doesn't show up on the same line. We can pad it. We could put like 20 here. And now there will be 20 spaces in front of that. We don't want to pad it from the left, we want to pad it from the right, so we put a hyphen here, and this will cause the opposite. Now it looks the same, but there are actually space characters here padding it all the way there. You can see that space character stops. So this is what we want to pad it. Now how much do we want to pad it with? Unfortunately, we're going to have to do some weirdness here. Notice that we have this string offline here. We actually use this string to calculate a length. We pad it with the variable, with the number 8 here. It's a magic number. It's not great, but we're going to just use that magic number and we're going to pad it with 8 minus 1, which is 7. Again, not ideal, but here we are. Hyphen 7s, and then we'll put the % here, and we can actually append the % right there. There we go. So it will pad the beginning with spaces. This will just print to the screen. We don't want that. So let's go ahead and save it back in the variable. So this one line will do what we want, but it's a very confusing line. Printf takes a -v flag, which says instead of printing it to the screen, write it to the variable. And the variable we use is ourself. So we just overwrite our own variable with what? With this. So pad this with 7 spaces, the original string with a %. A little bit confusing. Let's go ahead and remove the % here. But this will fix the issue. So if we pull back up tmux, we run the CPU visualizer, and we go down here and we run, let's run the one that pegs just one core. There we go. So let's blast that one core. You can see that the string has moved all the way over there. But look, when the string, or when it goes away, the % goes away. Those spaces have repadded the string without having to clear the entire screen. So because we're not clearing the whole screen, it's a lot faster, which is super nice. All right, so a bunch of people in the comments noticed this. They weren't happy about it. Some people ran it and it would just break. And the reason it would just break is because I expect you to be on Bash version 5.3 or higher, because I use a relatively new syntax. The syntax is somewhere. Let me go find it. Here's this syntax. So this command substitution syntax where we open a curly brace and we put the semicolon here and we save it into a variable. This is new in 5.3. You may have seen it like this before. Let me turn off that highlighting. There we go. You may have seen this before, where you open and close the parenthesis. This does the same thing, it just forks and exec a subshell, so this will work on lower versions of Bash. But the beautiful thing here, the reason why I didn't want to clear the whole screen to begin with is because we don't need it. If we don't clear the whole screen, if we just move the cursor home, we can just run visualize data on its own without storing it to a variable. And there we go. It's good to go. We don't need to clear the screen. We don't need this echo. We just move the cursor to the top, we visualize the data, and we sleep for 1 second. So it's way simpler, and this will work on older versions of Bash, which is super nice. So if I pull back open the tmux, go up here, and rerun the script, you'll see that it works just fine, and there's no noticeable difference. So there you go. That's a simple fix for people that want to use it on less than Bash version 5.3. All right, now here's something else I want to deal with. Notice that we have this function here, update window size. We even call update window size manually. Well, let's go ahead and take a look at that function. It's very simple. What we do is we check if columns is set. So if we have access to how long the person's terminal is, then we do a whole bunch of logic based on that. And we set this bar length variable. That's great. And bar length, we even defaulted to be a small bar length of 30, which is super nice. But what we should also do is we should just default our columns to 80 because we don't have this anywhere. So 80 columns is the same default. This is convention. You'll see this a lot. If we can't determine the size of a terminal, we'll assume it's 80 columns by what, 24 lines, I think. So we could put this here and that would be fine. But what I would rather do instead is if we go down here where we have this check, if it's defined, I would do this instead. Columns equals columns or 80. And then we can get rid of this whole if statement check business because it will always be set to something. So what this line does, a little magical line, we say set columns equal to columns. And if it's not set or it's set to an empty string, set it equal to 80. So we give it a default value. So when update window size is ran, we check if columns is set. If it's not, then we default to 80 and then we're good to go. Very, very simple. Also, there is an echo down here. This must have been during debugging. We don't actually need this, nor would we want this on the screen when we're resizing the terminal. So let's go ahead and trash that. And there we go. So now when we go down to update window size, everything can kind of stay the same there. So it should, let's go ahead and just check our work, make sure it all works as expected. If we run this, it should just work. And there we go, that's awesome. If I resize the terminal, cool, it resizes the CPU thing. That's really good, that's what we want. So resizing seems to work, no problem. All right, so that's most of the bug fixes down. As you can see, very small changes, not a big deal. The last thing I want to do, good practice here, is to run shell check on it because I haven't run shell check on it before and I'm trying to get better about doing this. And look at this, it already found issues. I like these issues a lot because it's previous and current. These were associative arrays that we created that we then changed to indexed arrays. And when you use indexed arrays, you don't need the $ in front of it. So it's really cool that this caught this. Because we changed from one data type to another, it means that we don't need to use this anymore. This syntax is totally fine as is, and shell check found that for us, even though we, through our iterative process, didn't notice it. So that's really cool to see. So 52 and 71. So if we go to line 52, we can change this to this. And if we go to line 71, we can change this to this, and it should all be good to go. Shell check reports, no errors with it. You can verify that with this, and we're good to go. Let's go ahead and do one last test just to make sure everything is above board, everything works. Hey, that's awesome. It looks like it's working. If I peg one core, there we go. One core is just completely blasted. If I let the scheduler peg a whole bunch of cores, hey, look at that. Looks good to me. Looks awesome. There's the bug fixes there. So let's move on to the actual network part of this, the interesting part of this. So we're going to be building a network visualization, like network utilization tool. So what do I mean by that? I'm going to model this loosely after bandwidth monitor NG. If you've ever seen BWN MG, I love this tool. I think it's really great. It gives me the name of the interface here. So LO for loopback, ETH0, and Docker. You can see how many kilobits a second were received, how many kilobits a second were transmitted, and the total where it adds the two up. I can press D and it will turn this one into bytes. We might not get that fancy, but I want to have output similar to this. Not exactly this, but I want output like this. So when I'm doing file transfers, I can see, like, am I transmitting a lot of bytes? Am I receiving a lot of bytes? We're going to make this in pure bash looking at the proc file system. In fact, take a look at this. The input is procnetdev. I wonder if that's going to be valuable information. All right, let's get to programming here. We have the CPU tool. Let's create the net tool now for network. So let's go ahead and add our shebang here, user bin env bash. A lot of people tell me I can do :E and I can get the syntax highlighting it. I like to right quit and then reopen the file because it's muscle memory. And I could talk about how I'm not trying to optimize every single part of my workflow. And sometimes people do need to slow down a little bit when it comes to programming. I know it's rich coming from me, I can talk pretty fast, but I think I'll do a video in the future where I talk about how we all just need to collectively slow down and not optimize every single part of our workflow, and then that'll segue into my feelings on AI and LLM, so look forward to that video. But no, I'm just getting distracted here, so let's go ahead and do this. So let's say visualize network bandwidth on a host. There we go. And check this out. I have my own little macro that I've had for over 10 years, and I've recently changed it because I'm a content creator now, and I have people that contribute to my code way more often than I used to. So it's super cool to see. So you can see this is when it was created, and here's a list of the contributors. I've put myself there. Obviously, I'm one of the contributors. But that way, if you were to make changes to any of my code going forward, and you were like, hey, Dave, I want to make some changes. That's cool. Just go ahead and put, you know, like bad cop, and then you can do like bad cop at hotdogstand.lol or whatever her email address is. I have no idea. So you could just do that. This way it makes it easier. I've had people make changes to my code and kind of be confused about the header and where they should put their name, if they should. And my response was sort of like, yeah, man, I don't know. So let me come up with something. So this is what I came up with. And yeah, hopefully this makes it straightforward if you have any changes you wanted to make to like any of this code or something. So what are we doing here? What is happening here? Well, let's take a look at our CPU code that we were looking at before. And we can see that one of the main things about this code is the proc file system. Look at this. We read in from proc stat. That's great for CPU usage because when you read proc stat, you get all of this, which tells me everything about a CPU. That's really good. Wouldn't it be nice if something existed like this for the network? Well, check this out. Proc net dev. Great name. And here we go. This is all the information we need. Look how beautiful it is. I promise it's way easier to parse. This doesn't look great to a human, but it's going to be fairly easy for a computer to parse. Although I do have some qualms with this file format, but we'll talk about that later. Now, of course, we can get the man page for this. You might be thinking, let me man proc net dev. This may or may not work on your machine. It probably won't. In my case, it tried to open it up, that file, in my man viewer. That's not what I want at all. So you want to view man proc net, man proc underbar net. There you go. And there's a whole bunch of files in here. procnet, procnetar, procnetdev. Hey, procnetdev. That's what we want. The dev pseudo file contains network device status information. This gives the number of received and sent packets, the number of errors and collisions, and other basic statistics. These are used by ifconfig program to report device status. The format is, and then it gives us the whole format here. So this is a weird format, but this is 2 lines. Interface, and then the receive amount of bytes and all this data, and then the transmit amount of bytes and all this data. So you can kind of see here, it's really hard to see. We'll break this down later, but ETH0 here has received this many bytes, and it has transmitted this many bytes. And ultimately, that's what we want out of the file. So we're going to use some bash finagling to get that out of the file. So let's go ahead and make net executable. If we run it, nothing will happen because it doesn't do anything. So what we want to do here is we want to look at proc net dev. That's the file we care about. That's what we want to look at. So if we run this, there we go. And we're done. The video's out. No, I'm kidding. There's a lot more to do. So the first thing here is there are 2 lines. These 2 lines are always the same. They're never going to change, or if they do change, we'll have to update the script. But we can throw these 2 lines out, is what I'm trying to say. So we're going to have to throw some information out. We don't need these first 2 lines. There's a couple ways we could do it. We could use awk, we could use head, we could use tail, I think, maybe. I don't know. We don't need to worry about those tools because we're going to be doing this in bash. So if we cat procnetdev, here's what we get. Instead of using cat, we're going to use this awesome built-in that I've talked about before, which is map file. So map file is built into bash. There's a whole big help page here that explains how it works. We'll go into details here later, but instead of running cat procnetdev, we're going to run map file, the name of the variable that we're going to set. So we'll call this lines, and then we'll read in from procnetdev. And there we go. That file has been read, and it has been stored line by line into an array called lines. That's all built into bash. It's super cool. We can inspect that array. We can do declare -p on lines, and that's really, really hard to look at, isn't it? So we can also use var dump. This is something that I wrote. I can link the source code in the description, but you can see that it's an array. Array spot 0 is this line. Array spot 1 is this line. So let's ignore these first 2 sections of the array. Look at this. Array spot this has this line. Array spot this has this line. Array spot this has this line. The beautiful thing about this is that map file has a way of discarding lines, which is super helpful. So if we look at the help page for map file, we have a -s right here. Discard the first count line read. So we can just ignore the first 2 lines. Very simply, we could run map file -s2 to discard the first 2 lines. And there we go. So now if we look at the lines, we can see that we just have the loopback, the ETH0, and the Docker. Now the interesting thing here is, look at this. They have the new lines at the end. We don't need the new lines at the end. We don't even want the new lines at the end. So we can give it -t. Remove a trailing delimiter from each line read. Default is a new line. So let's go back to our map file command. Let's go ahead and toss a -t in here. -t -s2. Save it into lines. Go ahead and run that. If we var dump it, it looks like that. If we run the declare command, it's a little bit confusing, but that's how it works. So we could also use printf. We could printf the line like this, and we could give it lines as input like this, and then it prints them separated by new lines. I know this is awful to read, but don't worry. Programmatically, it's going to be very easy to parse through. So let's go ahead and start doing this. Let's grab this code right here because we know it works. and let's pull it into our net tool. So instead of cat, we're going to run this map file thing. Now this can fail. So what I like to do is I like to do this, and then I can say fatal failed to read proc device. We don't need to specify which file exactly failed, because if map file fails, it will print a nice message with the name of the file here, so we don't need to duplicate the name of the file. So now this will fail if that read fails. Now here's the thing. Fatal is a function that we haven't defined yet, so technically this won't even work as is. So let's go ahead and define a fatal function, super useful. Let's just have it print fatal, print whatever arguments the user gave us, and write it all to standard error, and then exit with a failure code. So this fatal function is very simple. It'll just print what the user gave us with fatal in front of it, and it will exit the processing here. So if we put like echo done here, we can test it. So let me pull up that source code again, because I realized that was a little bit fast. We have our fatal function, we have our map file that will fatal out if it fails, and then we echo done. So let's go ahead and run that, and we get done. So it was successfully able to read the file. Imagine it wasn't able to successfully read the file. Imagine we gave it a file that didn't exist, like dev2 is something that doesn't exist. If we run this, look at this. We get this nice little error message. We get our fatal, and then it doesn't print done. So I think this is a helpful enough message. This will dissuade someone who's running on a machine that maybe doesn't have a proc file system. Maybe if I was running it on like a Mac or something like that. So let's go ahead and get rid of that so we don't keep making that error. But there we go. We have the data in an array called lines. Now that we have that, we can loop over it. For line in lines. There we go. This is the syntax to loop over an array in bash, and we could echo the line here just like we did before. And if we ran this, it's going to be that awful output again that's really, really hard to parse. It's not exactly what we want, so let's go ahead and start parsing this ourselves. One of the ways we can do this is with a read command. So we're going to run read, and we're going to give it -r so it doesn't do any special treatment to backslash characters. You'll find that you almost always want -r when you're running the read command. And we can read the fields one by one. So like foo, bar, baz, ... And then we can read that in triple less than from line. So this is a special syntax in bash called a here string. It will pass this entire string with a new line to the read command here, and read will break it based on white space by default into all these separate variables. That's a little bit confusing because you might be thinking to yourself, well, what are the variables exactly? Well, don't worry. We have the man page, man proc net. So if we go down here, we can see what the file looks like. It will be the interface name, the receive bytes, the receive packets, the errors, the drop, the FIFO, the frame, the compress, the multicast, blah, blah, blah. There's a whole bunch of stuff there. So this is going to be a little bit gnarly, but bear with me. Instead of foo, bar, baz, let's go ahead and call it iface receive bytes, or rx bytes. And then I think there was a whole bunch of stuff, and then one of them was transmit bytes, and then a whole bunch of stuff. Now, I don't remember how many there were, so we're going to go ahead and have to count this manually. So the receive bytes are here, so that's one, and then there's 1, 2, 3, 4, 5, 6, 7, and then the 8th one here. So it looks like we're gonna have, I already lost track of the count. So we're just going to hope that this works. And we're going to do it, what do you think, one more? That sounds about right, right? So it's a little bit confusing and it's a little bit ugly, I understand that. But now that we have this here, instead of echoing the entire line, we could echo the iface, and then let's echo the rx bytes and the tx bytes. So if we run our script now, we can see that, okay, well, we're getting 0 there. So that's not right. Obviously, I was off by something in some direction. So let me actually count this now. 7 underscores. Wow. Yeah, this is super annoying. Okay, I had 6 underscores and we need 7 here. So yeah, as you can see, kind of hideous. Now, the nice thing is we're not using these, so we can throw these out. Look at this. This is a lot easier to understand. Here's the name of the interface, here's how many bytes were received, and here's how many bytes were transmitted. If you're confused and you're like, wait a minute, that interface has received this many bytes? Yes, since it was powered on, that's how many bytes it has received. It's a nice big 64-bit integer, I think, and since it's been powered on, this is how many bytes have been received on this interface. So if we're gonna calculate utilization, we need to sample this data, sleep for 1 second, sample it again, subtract one from the other, so we calculate the delta, and that's how many bytes were sent in a second. So now we have a nice bytes per second metric, but we'll worry about that later. For now, we have the interface name, the bytes, and the bytes, the receive bytes and the transmit bytes. Notice this though, that colon, where's that colon coming from? Well, the colon is here, part of the name, which is kind of annoying. I don't know why it's the case. It's pretty ugly. So this colon is actually being considered part of the interface name, and it's not. I think it's just ugly. So let's go ahead and get rid of that colon. So we have this iface variable here. All right, so we can use parameter expansion here to say iface %, colon, close it. So percent sign means starting from the right, delete whatever character shows up, and the character that we want here is a colon. So this will get rid of that colon here. So if we rerun it, let's go ahead and rerun that here. Look at that, there's no colon. We just have the name of the interface, the amount of bytes received, and the amount of bytes transmitted. So this is way easier to understand already, which is super nice. Now, I'll be honest, I don't love this. This is not the most beautiful thing in the world. So we can rewrite this. We can do things a little bit differently, and I think it's a little bit cleaner. Some people may not. You're gonna have different thoughts on this. This is just stylistic. I would prefer, instead of being written out like this, let's go ahead and duplicate this line, if we were to read everything into an array. So we can do that simply. We could call this like info, and it will be an array called info, and it's an array because we're giving it an A. The dash A makes it an array. So instead of storing it like this, we're just gonna store everything in an array called info, and then it's our job to pull that information out of it. So the I face will be info at array spot 0. The RX bytes will be info at array spot 1, and the transmit bytes will be info at array spot what 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. So there you go. Same information expressed slightly differently, but then we have less of a long line and more of multiple lines of code here. But maybe this is easier. I prefer it this way, so we're just gonna leave it like this. If I rerun it, it should be exactly the same. There you go, super easy. So read has the ability of loading right into an array, which is super nice, super helpful. So what are we doing here? We have this information. We have the name of the interface, the amount of bytes received, and the amount of bytes transmitted. That's great. We have to sleep for a second and then resample this and get the data again. So we need an old and a new. What we can do here is we can store this data. And I'll show you what a data structure might look like for storing this. So what instantly jumps into my mind is using some sort of like hash map type of data. This is not valid bash syntax. We're just sort of brainstorming right down here. But if I were in JSON, I would imagine something like this. I would imagine eth0 would have a transmit of 500 bytes and a receive of 400 bytes, something like this. This is what I imagine. And then this would be duplicated for each one. So the LO for the loopback, the Docker 0 was the other one I think I had. I'm imagining some sort of data structure like this, where we have the name of the interface and then the metadata about that interface here. Now we don't have nested data structures in bash, so we have to smush this data together. So instead, all we can do is store strings. That's all we have here. So we're gonna have to store something like this. It's not pretty, but that's what we'll have. We'll have a key value store where the key will be the interface name and the value will be all the information we want to store separated by some sort of separator. In fact, we're using a comma here. Let's just use spaces because bash can break spaces automatically. We could use a comma, but with spaces, we don't have to make any changes. Notice that this read statement up here, we didn't need to tell it to use white space. It used white space by default. If we wanted to, we could do ifs equals comma. Now it's suddenly splitting it on commas. That's great, but we don't need that. We can split on white space by default. So our data structure will look like this. We'll have a key, which is the interface name, and the data will be a string version of the values that we want to store, and then we can break that information out later in the future when we need to process it. Declare -A data, and then we'll set it equal to a blank array. So we'll initialize it to be nothing. So here we go. We have an associative array called data. Now we can store information in it. So right down here where we echo it, instead of echoing it, we can say data $iface equals, remember this is a string, so we have to put everything together ourselves, rx bytes tx bytes. So we're storing it as a string. So there we go. Now we have that data. That's really good. We're not doing anything with that data. If we were to run this code, it would print nothing. It stored the data, but there was nothing to print out. We could do a declare -p on all caps data here, and we could rerun it, and we can see that it's lowercase p and not uppercase p. Declare -lowercase p on it, run it, and we can see this is what we're storing. The loopback interface is 0, 0, Docker has 0, 0, eth0 has this many and that many. So cool, that makes sense, that looks good to me. What we need to do now is we need to sleep for 1 second and then redo all of this logic again. So let's rearrange some things real quick. Let's move this data up here and let's move this map file closer to where it's called. So now we have this. Let's go ahead and grab all of this logic and bring it down here. This is the best kind of programming. It's called copy and paste programming. Don't worry, we're gonna clean all this up, but for the sake of education, it makes sense to copy it all first and then show how to condense it. Because if I just show you the condensed version, it's gonna be very confusing. We're iterating on this the way a human would. So once we get down here where we have all that information, instead of storing it, we want to extract the old information from it. So let's go ahead and say old equals data at spot iface. So this will be the old data. Remember, it's a string, so it'll have 2 values in it. We need to break that string apart. Luckily, we can with the read command. We store it as old rx. That's not what I wanted. Whoa. You ever accidentally hit caps lock and then Vim starts acting crazy on you? I thought I had caps lock disabled on this machine. Apparently I don't. I have to do that. It's usually one of the things I do. I don't set caps lock to escape. A lot of people do that. I just disable it. I don't like the caps lock key. I'm never going to use it. All right, so where were we? Old rx bytes and old tx bytes. Very verbose variable names, but hopefully it makes it easy to follow. Read that in from the old string. So now we have old rx bytes and our current rx bytes, old tx bytes and our current tx bytes. So now we can get the delta, the drx bytes, the delta received bytes is what I'm saying here. I know I'm repeating myself a lot, but I find it makes it easier to follow along and learn this stuff when it's really hammered in there. So the delta will be what we have currently, which is rx bytes minus old rx bytes. So what we have currently minus what it was 1 second ago will tell us how much it's changed in that 1 second. So we do this. Let's go ahead and copy and paste that, change the R to a T, change the R to a T, change the R to a T. And now we have the delta of RX bytes, the delta of TX bytes, and we can also have the delta total bytes. Remember I talked about getting a total. We'll worry about this later, but we just add those two together, the RX bytes and the TX bytes, and there we go. There's our delta total for that interface. So now we can echo iface colon drx bytes d tx bytes d total bytes. There we go. So let's go ahead and run this code now. Now I know it's very verbose, but it should sleep for a second and then give us an error. That is awesome. So let's see what we did wrong. drx byte. Oh, I didn't put a plus here. There we go. Wow, that's incredible. So if you want to yell at me in the comments, go ahead. Also, while you're down there, go ahead and make sure you're subscribed, okay? Click that subscribe button. I want to get this channel over 100,000 subscribers. At the time of this recording, I have 90,000 subscribers. I am so close to that silver play button. It's such a vanity metric, but that is what I want, and I'm going to be showing it off like you wouldn't believe. So thank you for hitting that subscribe button. Let's jump back into it. All right, we got that plus sign. Let's go ahead and right quit, and let's run it. So again, it should sleep for a second, and then it should print. Here we go. Look at this. There's the delta. So these numbers are way lower. If I'm reading this correctly, then 10 kilobytes were received, 4 kilobytes were transmitted, and the total would be 14. That seems fine to me. Sure, I don't know. This machine's not doing too much, but there might be some sort of processes sending and receiving data. That makes sense. I'm also SSH'd into it, so there is data being transmitted back and forth. Now, there's a lot of different places we can go here because we have good information. We have them in bytes. We might want to change the way we display it to the user. But I figure the first thing that makes the sense to do is clean this up. Because right now we have a lot of duplicated code. That's not great. We can condense this all into one loop. So let's go ahead and do that. So let's move this sleep all the way to the bottom loop down here, because the bottom loop is the one that we're going to be using. So we read the file in. We loop over each line and we extract the data from the file. So this is our current version of the data. Then we grab the data that is old, the data that we have recorded previously. So that means this might not be set, right? Imagine this is the first time this loop is running. If this is not set, if -z old, meaning old is not set or it is the empty string, then we need to print something to the user, echo iface old data not found, and then we'll continue. We'll just go to the top of the loop. We'll try again. There's no sense in trying to continue. We've never seen this interface before. Then we'll read the old data. We'll do all our logic here. We'll print it out and we will sleep here. Now that I'm rereading this, I don't want the sleep to be per interface. I actually do want the sleep down here. So what we have here, let's go back to the top. We have this initial loop where we read the data initially. Let's go ahead and just completely trash this. Except for this one line. We want this line. This is where we save the data. So if there was no old data there, then we continue. Before we continue, we want to save the data. So this is a little bit confusing, and I'm going to explain what's going on here. So forget the fact that there used to be 2 loops. There is now only 1 loop. We read the entire file into a variable called lines. We loop over the lines that we see. We load that line into an array called info. We extract all the information out of it. This is where we do our check to see. Check if we've seen this interface before. Store the new data no matter what. Stop here if we haven't seen this interface before. So does this make sense? We have to do it in this order. This is very important. We extract the data that we've seen before for this interface, and then we store the new data no matter what. We overwrite what was there. We store the new data no matter what, and then we check. Did we actually see something before? If we didn't see anything before, we can't continue. We stored the new data, so the next time this runs, we'll have it, but we have to stop here if we haven't. Now you might be thinking, what do you mean next time? We get to the bottom and then we sleep one and then the whole thing exits? Well, yeah, because we want this whole thing to be in a while true loop. So an infinite while loop. So let's go ahead, bring all that up here, close this, and now everything has been moved into an infinite while loop. So let's move this into there, and let's review what we have. So in an infinite while loop, we read the data in from the proc file, we process each line, line by line, printing out the information per line, and then we sleep for 1 second, and then we do it again. So very, very simple. Let's go ahead and rerun this and make sure it works. So, oh boy, there's a lot of code here. I can't show all this while I'm running it. But look at this. See, it showed us there was no data found because there's no data found the first time we run it. But now you can see there are 3 interfaces every time. And here's how much data is being sent. So we're receiving 5 kilobytes, 9 kilobytes, 2 kilobytes. We're transmitting this many, so transmitting way less than we're receiving. Wait, hold on. Did I say that backwards? One of them transmits, one of them receive. I might have said it backwards. I think we're transmitting more than we've received. Transmit is first, right? We save Rx first, and then if we do man proc net, we have receive first. Okay, so receive is first and then transmit. So Rx is first and then transmit. Okay. I don't remember if I said it wrong or not. If I did, luckily everyone in the comments will yell at me because I tend to get these things backwards. So hopefully not. But we can also verify this. I can verify this against a tool that I know works, bandwidth monitor, and we can see, okay, look, the receive is around 10, 12. It's a higher number than the transmit. We're transmitting way less than we're receiving. So it lines up with what we're seeing with our tool, which is nice. Now our tool is not exactly the prettiest tool, but hey, this is pretty cool already. This is a lot of the data that we could possibly need. So I think the next step here is that we can move all of this into a function. Because there's a lot of stuff here, as you can see, it's a little bit nested, and if we were to nest all this inside like a main method, for instance, it'll get a little bit gnarly. In fact, let's go ahead and do that. Let's move all of this into a main function. So I'm gonna indent this whole thing. So now we have this main function here. All of this is indented. Close the main function, and then we'll call main with whatever arguments the user gave us. So look how far indented some of these things are. I know guys, a lot of you guys get upset that I use tabs as my indentation. Yeah, I like it, so I don't plan on changing that. But as you can see, this goes over 80 columns, and I kind of have a strict 80 columns rule. So I'm gonna go ahead and we'll put a backslash here, 1, 2, 3, 4, and there we go. We can put this on 2 lines. So this will map the file and then call fatal if something fails. But down here, where we loop over each line, instead of having all of the logic here, we could move it into a function. So what we can do is we could make a nice little function called process iface to process the interface, and then we can choose what data to give it. So we do a little bit of parsing here, which is nice. This function does not have to be aware about where the data comes from. It doesn't have to understand how to parse a proc file. That's being parsed up here. This function is just responsible for processing the data. So let's say the interface name, the Rx bytes, and the TX bytes. So that's what this function will take. And let's go ahead and actually define that function. Process iface, and it has 3 arguments. It takes the iface as $1, and then it takes, what do we say? Rx bytes down here, and this will be TX bytes, and this will be $2 and $3. So there we go. Now we have our process iface function, which means we can take all of this code right here and move it into the function. So we're starting to clean it up a little bit. So if we move it here, look at this. We've killed 2 levels of indentation, which is super nice. Now that we're inside a function, we have to be good. So we have to go through here and start localizing all of our variables. Otherwise, these variables will be global. It's not a huge deal, but you can get into some sort of collisions with names. So we'll put local in front of it. This one's not local. This one's specifically reaching the global variable data. So we're not going to put the word local in front of it. But other places here where we have old, we have these. So local old RX bytes and old TX bytes will go there. We can go down here. We have to declare these as local too. Local D, RX bytes, D, TX bytes, and D, total bytes. Again, not the cleanest thing, not the nicest looking thing, but this is how we make sure that we don't bleed into the local scope. Actually, now that I write it, why don't I just do it like this? Hold on, I'm making things more complicated than they need to be. There we go. That's simple enough to understand. So there we go. So there's a couple of last things to do. We have this also main method now. We have to make sure that we don't bleed into the scope there. So we can do a local -a on lines, because remember, lines is an array. So local -a will initialize it as an array. We can do a local line here, and then just put some local things here. So local array for info, because we're using in this read call here. And then all these will have to be local. And that's it. That's all that's required here. So look at this. This is a lot easier to understand. We go into an infinite while loop. We read the proc file. Read proc file. Loop each line in the file. And then process the interface for it. And then sleep for a second. Very, very simple logic. And the nice thing is when we go ahead and run this, it should just work. Well, it should, but it gave us a nice little error message there. Okay, I know exactly what's going on. I think I used continue. Continue makes sense if we're in a loop, but now that it's in its own function, it doesn't make sense. So let's just go ahead and early return here. We can give an exit status here of 1. We're not actually consuming it anywhere, but it's good practice because we're returning with a failure. So if we rerun this, there we go. Now it works as we expect. The beautiful thing about this is because we've cleaned the code up a little bit, we can make things a little bit nicer. So before we go through and actually loop each line, we can just echo a new line here. When we're done processing each interface, we can just echo a line here. So what does that do? Well, look at this now. Suddenly, this is a lot easier to understand. We can actually see a little bit of grouping going on here. So that is super nice. What we can also do is we can format this data, because if we were to look at, let's use a bandwidth monitor again, you can see it's all kind of nicely formatted and spaced apart. We can do that ourselves, and we can lean on printf to do that. So instead of doing the echo here, we can run our own little printf instead. So we could say, %s and then a new line, and then we could just put the interface here. Well, let's build this out a little bit, because we've already done a little bit of padding from the CPU command. So let's reuse some of that logic. So here we could just, let's pick a number, let's say 15. This will be the interface. All right, on the fly, I'm actually trying to figure out how to do this. So I think what we'll do is we'll pass the data in first. So RX bytes is first, transmit bytes is next, and total bytes is last. So we have 4 variables: the interface, receive, transmit, total. So we have the interface, receive, transmit, and total. And if you're like, Dave, where are you getting 15 from? Arbitrarily. I've arbitrarily picked 15 characters, and we're going to see what it looks like. So let's go ahead and get rid of this echo and use this printf instead. We can do a little backslash here, and we can put these on its own little line, so we're not going over 80 columns. Let's go ahead and rerun this and see how it looks. Hey, look at that. That is way cooler already. That is that little change made a huge difference here. I like this a lot. This is awesome. All right, you know what? So now that we're here, let's actually, I got a new idea. We're gonna be doing some programming on the fly. We have this printf here. Let's go ahead and copy and paste that printf here. So before we loop over each line, we can put it here, and we could say something like, hear me out. Interface, receive, transmit, total. These are just strings. There's nothing special about them. So if we run this, we should have a nice little header at the top. Look at this. Interface, receive, transmit, total. That is pretty slick. I like that. I think that's really cool. Now, of course, this printf has been copied and pasted. So what we can do is we can go up here. I copied it to my clipboard. We're going to paste it down here, and we'll store it as a variable called format. So we'll just store this string as a variable called format. It's a format specifier. Now where we call printf, instead of this, we can call format here. And if we do that, they can all go on the same line. Doesn't really matter. Let's go here, change this to format, put them all on the same line. And do I like them uppercase or do I like them lowercase? Let me think. I might actually like the lowercase better. If you guys have noticed, I kind of use all lowercase. Ooh, I like that so much better. Oh yeah, we're sticking with that. That looks way cooler. I like it. I know some people won't like it, but hey, it's my tool, all right? I write it how I want it. So that looks cool to me. I like this. This is really cool. All right, so what's next? Let's talk about units, okay? Networking units are really weird. Computer units are really weird. I don't have time to deep dive into all this, but you ever notice like when you get a hard drive and it's like, oh, this hard drive is like a terabyte, and then you format it and you have like 930 gigs of available space on a 1 terabyte drive, and you're like, why is it not 1,000 gigs? It's because sometimes it's divided by 1,000, sometimes, or multiplied by 1,000, sometimes it's multiplied by 1024. Sometimes it's 2 to the 10, which is 1024, which is really close to 1,000, but not quite. So sometimes you have the SI units, which are out of 1,000, and sometimes you have out of 1024, and it's really confusing, and it causes a whole bunch of issues. With networking, they don't typically work in bytes. You're going to be working in bits, you know, like kilobits per second and megabits per second. You might also have kb bits and megabits. I'm probably butchering those explanations. This is one of those things, like I said, I don't have time to deep dive into all that, and I also don't even fully know it that well. But what I do know is how to turn this data into something we're used to seeing. So we have our RX bytes, our TX bytes, and our total bytes. We're going to turn them into bits. So we have RX bits, TX bits, and total bits. And the way we do that is we're going to take the DRX bytes and we're going to multiply it by 8. There are 8 bits in a byte when it comes to these networking packets. So put a D here and put a D here. Notice how I'm jumping all over the place and kind of just changing things, not one at a time, but kind of bouncing around. Don't program like I do, because this will totally lend itself to writing bugs. I'd be amazed if this was all right on the first try. DRX bits is calculated by DRX bytes times 8. DTX bits is calculated by DTX bytes times 8. D total bits is calculated by D total bytes times 8. That looks good to me. That makes sense. So let's go ahead and turn bytes into bits. So there we go. Now we have bits per second as opposed to bytes per second. So it's just multiplied by 8, but we can see that we're getting like, okay, 80 or 33 kilobits per second, 21 kilobits per second. That's what's going on here if we divide it by 1,000. So we can still do a little bit more formatting here. So now that we have the bits, wouldn't it be cool if we had actual units that went with it? So let me show you what I mean. Imagine if for the delta of RX bits, we just had RX equals the delta of RX bits BPS, bits per second. We had something like that. Then we can copy and paste this for all 3. So we have this, and then we have total. So DTX is this, and D total is this. So now if we change that to output those things, so we have RX, TX, and total. So now, if we run this, we will have this kind of an output, which will have the BPS in there. It might be a little bit gnarly, it might be a lot to look at, but it might be useful to have the actual thing there. If we look at, bandwidth monitor NG here, it does the same exact thing, how many per second. And this one, it looks like it's actually kilobytes. I'd have to double check the units on this. But yeah, if we run it like this, we'll have that there. It's not useful right now because it's always bit per second, but wouldn't it be nice if it was kilo and megabits per second? Let's go ahead and do that next. So where we have RX, instead of setting RX manually here, imagine if we just called out to a function we had. So we have a function called format bits. We'll give it the RX bits, and it will return a string that has already been formatted to us. Now, this function doesn't exist, of course. We have to go write that function. But let's go write that function. So let's make sure that this one gets the TX bits, and the total here gets the total here. So if we call out to this function format bits 3 different times, well, format bits, we can go ahead and define up here. Format bits, we'll take the bits as $1 here, and then we can do some really, really simple checks. If bits is greater than 1,000,000, then look at that. We have megabits. Very, very simple. So to return data to the user, we can just echo bits divided by 1,000,000 Mbps. There you go. Now we can add another one. We could say elif bits is greater than 1,000, then it's kilo. So we could do this, bits divided by 1000, and then kbps. There you go. And then we can just have an else here, which is the catch-all, which was just bits. So this would be bits BPS. Now notice that BPS is 3 characters and kbps is 4 characters. Let's go ahead and put an extra space here. This will just align everything for us. So if we have this, now we have this format bits function. It can handle megabits, kilobits, and regular plain old bits per second. So let's go ahead and rerun this and see what it looks like. Look at this. So this is really, really nice. We can see that ETH0 is doing 15 kilobits per second when the rest are doing 0 BPS, or this one's doing 4 kilobits per second. We could make this customizable. We could make it so you take a flag if you want bit output or kilobit output, but I want to show how easy it is to format this data when we just use nice little reusable functions like this. Now, technically, if you're watching this and you're probably like, Dave, there are so many better ways to do this. I could make an array here where I could take bits and divide it by 1e6, and then I can check if that's greater than 0, and then I can automatically have it append this, which I store in some sort of data structure. Yes, there are definitely more efficient ways to write this function where we could handle all of the possible ways of dealing with it. I choose to go with this one. It's very simple, it's easy to teach, and it's very easy to understand. Because we don't have complex data structures in Bash, it's kind of annoying to make like some sort of an array that has that data plus the suffix. You might disagree, and if you find a really cool way of doing it, go ahead and make a pull request if you find a really, really simple way to understand it. So I just don't want to overcomplicate it when it comes to teaching this stuff. I figure this is a really simple way to do it, and if someone wants to add to it, it's very clear what's going on here. So if you find a clean way of doing it and you want to make a pull request, hey, pull request welcome. Go ahead and add your name to the contributors list up here. But for now, I figure for educational purposes, it's simple enough. Look, if it's over 1 million, then we divide it by 1 million and we have megabits per second. What an easy line to understand. All right, so what's next? Where do we go next here? Well, I think the next thing that makes sense is if we look at that CPU tool again, notice how it blocks out the entire screen and then gives us the information at the top. And when I control C, it's gone. Let's go ahead and give the network tool the same logic. So we're going to vim both files here. Let's pull up the CPU tool and remember how we did that. Because in order to accomplish that, we need some ANSI escape sequences. So we're going to reuse some of them. So look right here. This is the CPU tool that we wrote before. We print these weird, bizarro things to the screen. This is an escape character, and this is an ANSI escape sequence. My terminal understands this. My terminal will know to enable the alternate buffer, to hide the cursor, and to move the cursor home. So let's go ahead, steal this logic, and go over into our code here and put it right in the main method. So right before we call that infinite while loop, we're going to run this stuff right here to enable the alternate buffer, hide the cursor, move the cursor home. We're not going to run this yet, okay? There's still more to do. Let's pull back open this first thing, and we can see that we do some work here. We trap the exit signal with a cleanup function. So let's go to that cleanup function. Look at this function right here. It's called cleanup. It disables the alternate buffer, and it shows the cursor. So it undoes what was done before. So let's copy this cleanup function and put it right here. So take a look at this. We enable the alternate buffer, hide the cursor, move the cursor home. Then we go into our infinite while loop of processing data. Once we're done, we need to trap this so this actually runs when it's done. Once we're done now, we will run this, which will disable the alternate buffer and show the cursor. So it undoes what we did before. Now, I want to do some even more cleanup here. I don't love this is called cleanup. I would prefer, here's what I would like. I would like this stuff to live in its own function called init term to initialize the terminal for drawing. And then this should live in dinit term. There we go. So we can call init term here, and then we can dinit term here when it's exited. I also still don't love this because we can get into some weird race condition. I would prefer to do it in this order. I would prefer to hook up the exit handler first before we do any initialization, because imagine the scenario where the user presses Control C really quickly. It's not harmful to run this. You could run this at any time and these are not harmful. They'll undo what was done only if it was set that way. So if you show the cursor when it's already shown, not a big deal. If you disable the alternate buffer when it's already disabled, not a big deal. So I like to do it in this order to avoid any sort of race conditions. We'll set this up so we will deinitialize the terminal when the exit handler is ran. So if we Control C it, if it exits naturally, whatever. And then we initialize terminal by doing all this. So what do we have? Let me show you. Let's go ahead and run the network tool and watch what happens. Brand new screen. It shows up here. I Control C and it's gone. That's amazing. That's fantastic. That is what we want. And as you can see, we don't really want this whole thing from happening. Notice how it's going down and drawing more and filling up a whole buffer there. We don't actually want that, but that's an easy fix because we do all this stuff. We echo, we print the format, we call sleep one. What we should do is copy this. Remember where we moved the cursor home? Let's go ahead and take this line and put it right at the beginning of the infinite while loop. So the first thing to do when we start processing is move the cursor home. This moves the cursor to position 0, 0, the top of the screen. So now we run this. Look at this. We keep moving the cursor back to where it was, so it keeps overwriting the data here. So this is updating live. It's in its own little world, its own little buffer. I control C, and it's gone. I mean, okay, it still looks like it's up there. Here, let me hide that. I'll curl my website. If you've never seen it before, curl ysap.sh. There is my website. That's beautiful. Let's run the net tool. It takes over the screen. We get this. We control C, and look, my website's still there. So there's your proof that the alternate buffer is working. All right, now there's one last thing I think we need to do here, which is very obvious if you've been watching. Look at the CPU. Look at this. There's color output here. I like the way the color looks. Well, let me run the net tool. There's no color output here. That's really boring. So let's go ahead and copy some of the color from the CPU to the net tool. So at the top of the CPU script, we have this. We have this logic right here, and we're going to copy this logic exactly. I will explain this logic, so don't worry. We're just going to copy it for now. I'll explain what's going on here, but this gives us access to these variables, color 1, 2, 3, dim, and reset. So let's use these colors. Now, there's a couple different ways we can use these colors, but what I want to do is find out where we actually print something to the screen. So for instance, down here, we print that header. Right here, we print that header where we just print interface, receive, transmit, total. That's really great. We can go ahead and we could do something like dim here, the format string, and then reset. We can sandwich the format string between a dim ANSI escape sequence and a reset ANSI escape sequence. So then if we rerun this network tool, look at this. This top line is grayed out, so it's not as bright as the other one. So that's pretty cool. That's kind of awesome. Now, if we do that, we could also do something like with this printf, where we print for each interface that we've seen. We could do something like, I don't know, color 1, and then sandwich the whole thing inside its own color. So if we run that, we get this, where they're all red. Okay, so color 1 is hideous. Let's not use color 1. That's stupid. I don't remember which color is which, so we have 3 colors to try. What does color 2 look like? That's fine. What is color 3? I think color 3's got to be cyan, right? Yeah, I like that better. The only downside is, as you can see, everything's the same color because we've colorized the whole format string. So we have the interface colored, and then this stuff is colored. I would prefer the interface to be colored and then this data to not be colored. I don't want to overwhelm the user with color. I just want the interface to be colored. So here's the obvious play. Okay, we call it color 3. Let's get rid of that here. Let's get rid of that here and throw color 3 here and then reset here. Now, here's the thing. Look at what's happening. Do you see how messed up the formatting is? What's going on? When printf is trying to do the formatting, remember how I set everything to 15? The printf format string has 15 set here everywhere. It's trying to make that interface take up 15 characters. And you might be thinking, okay, Dave, these aren't large things, so why are they over 15? It's counting the ANSI escape sequences as part of the character count, which sucks. And there's not an easy way around this. So I didn't originally plan on doing color output in this, so this is going to be a little bit longer in the video, but hopefully you guys are enjoying this. So we're going to figure out how to do this the right way. I don't have a great solution for this. Let's clean up some code and then we'll jump back to the fix, okay? So first things first, I think we're only using color 3. Yeah, so I don't plan on using color 1 or color 2. So let's get rid of that and let's just call this color, just all caps color. So color 1 and color 2 are gone. This one will be all caps color. And let's go find where I used color 3 and just change that to color. There we go. And I'll explain this line for anyone who's a little bit confused. These are ANSI escape sequences I'm setting it to. So color is just set to 36M, which is cyan. Dim is set to 2M, which dims the color. And reset is 0M, which completely resets any formatting. What I'm doing here is I'm checking -Z, no color. This is a bit of a double negative. We're saying if no color is not set, or another way of saying that, if the user wants color, then we will set these variables equal to something, which are color codes. And if they don't want colors, then we will set them equal to nothing. So we honor this global environment variable called no color. So if we were to run net, as you can see, yeah, the formatting's wrong. Ignore that for now. We get color. But if we were to rerun this with no color equals 1, you can see that there's no color output here, which is great. And we get proper formatting. So that's really great. So like I said, I don't have a beautiful solution. Here's the solution I come up with. And if you guys have better solutions in the comments, I would love to hear them. Let's do title format and data format. So title format and data format. Now you may be wondering why I'm separating them, because now let's go ahead and let's call, this will be, for each interface, we'll be using the data format, and for the actual title, we'll use the title format. We'll get rid of the color codes here, so we won't embed the color codes. So title format is used there, and data format is used there, and let's get rid of these embedded color codes. Okay, so no more color codes at all. We have our title format and our data format. So now we can put the color codes in the format string. Again, I don't love this. If anyone has any better solutions, I am totally open to them, but this is kind of how I would approach it for now. Because we're using double quotes now, we have to escape these backslashes, but there we go. Now we can put color codes here. So I could put dim here, and I could put reset here. Of course, I'm realizing now if I want to use those variables, I should probably put them down here when they're actually defined. So make sure you do things in the right order. And then for the data format, I could do color around the interface name, reset it here, and there we go. So now just the interface will be colorized that cyan color, and all of the title will be dim, assuming this all works. So let's go ahead and rerun that. I ran it with no color, so that's not going to be helpful. Oh man, there we go. Hey, that's great. Look at that. The interfaces are colored, just the interfaces. We're not overwhelming the user with color. And we have, look at that, bits and kilobits. This is beautiful. This is awesome. So this is great. The downside to putting the color code in the format string is that we can't colorize the output based on what's happening here. Because a cool like V2 for this would be if bits per second were one color, kilobits were another color, and megabits were another color, so you could quickly see if something's using a lot of bandwidth. But for now, we're just going to leave them white as is. So yeah, I think the last thing here, which is so funny that I waited till this moment, I think the last thing is to test this and make sure it's working in a way that's a little bit clear to understand. Because like, take a look at this. Okay, you just have to trust me that data is actually flowing, right? So let's go ahead and do this a little bit differently here. All right, so here we go. We're logged into Void, and we are running the network tool up here. So you can see the network tool is running. That's all well and good. That makes perfect sense. Let's go down here and do some actual testing, all right? We're on the same machine. Let's go ahead and make a big file. Let's make like, I don't know, a 500 megabyte file. So we'll use dd, the input file will be dev0, output file will be bigfile.dat. There you go. The byte size will be 1 megabyte, and the count will be 512. We'll make a 512 megabyte file. That's not right, capital M, there we go. So now we have a 512 megabyte file locally on this machine. Let's go ahead and SCP it out. Let's SCP this file to Arbiter. This is just another machine I have on my network. So if we SCP this out, we should see the transmit skyrocket for this. So look at this. The transmit, oh wow, that was a really fast transfer. We only saw it for a little bit. Let's make a slightly bigger file. Let's make, I guess we could do 2048. Let's do 4096, so a 4 gigabyte file. And, is there enough room on this? This is a virtual disk. Let's just hope there's enough room. Let's go ahead and re-SCP that file. So transmit skyrocketing, look at that. 1.5 gigs a second, awesome. And we're doing a little bit of receive, but that's just because it's TCP, it's going back and forth. That makes perfect sense. So yeah, that is the transmit being really, really high as we transmit this very large file over to Arbiter. That is really, really cool to see. So now, once this is done, we can SSH into Arbiter, and we can do it backwards. We can SCP big file back over to Void. And this should do the opposite. Now the receive of Void, yeah, look at this, we're receiving at 1.7. Yeah, so the receive is just completely being flooded with data. So there we go, it's working. Like, I knew it was working, but I figured it'd be fun to actually show this and verify that it is working, and you can test this on your own machine to sort of simulate network traffic. Well, simulate, actually make network traffic. It really is network traffic. Cool, awesome. Let's go ahead and remove those before we forget, because that'd be annoying. And I guess one last thing to try is Oh man, should we turn off interfaces? This could be a lot of fun. This could be a lot of fun. Okay, let me think about this, because we could do, what was it, if config docker 0 down? Docker 0. So let's just bring docker down. Now it's down, so it's all zeros. That makes sense. What if we go up here and rerun it? Does it still show up? Oh, it still shows up. It just doesn't matter if it's up or down. Okay. What if, you almost got me. I was going to say, what if we shut off ETH0, but then we won't be able to SSH into it. Let me think about this one real quick. All right, so I've logged in. So Void is a virtual machine. I've logged into the hypervisor of it. So if I do this, we can see that Void is running. Okay, that's awesome. Let's zadium console into Void, and let's do this as root. And so now we're connected to the console. So if we log in as root here, there we go. We are logged in this machine as root through the console, so it won't be bound by network fluctuations. So, so I have an idea here. Let's go ahead and let's go into home Dave Viz, because that's where the tool actually is. And we can run the network tool over here. And so this is running over the console. Let's go back over here and let's turn ETH0 off. So this will completely hang. This is broken now. This is broken. The network is off. Let's go over here. Look at that. ETH0 is completely down to 0. We are not using any data on it. That is so cool to see. That is awesome. It makes perfect sense. So now I guess we could just bring it back up. Do I have to reconfigure it? Hopefully not. I have no idea if there needs to be some reconfiguration that happens. Maybe not. I mean, it looks like it's transmitting data, right? So did it get an IP address? Oh, wow. It came back up. Tmux survived? No, it did not. I'm lying to you. The terminal needed to be refreshed. It's not actually in Tmux. We're on my Mac. Okay, that would have made no sense to me. Okay, we can SSH into it. We can pull back up the Tmux. The Tmux survived. That makes sense. I did not expect that connection to survive. And it didn't. So that's good, because I would have been really weirded out if it survived. So there you go. There's some fun tools. There's some fun checks over there. Let's log out of the console before I forget. And is it that? There we go. Log out of that. Cool. So there we go. There's a really cool network visualization tool written from scratch in Bash using built-ins. I think it does fork out to sleep. I guess that'd be the only external tool it forks out to. But we have this beautiful visualization tool in Bash, and it reads the proc file system, so we can actually get data off of like a Linux or any sort of system with a compatible Linux file system. So here we go. This is super cool. This is awesome. I'll put the code online. I'll have it linked below. Yeah, so if you made it this far, thank you so much for watching. You guys are awesome. Go ahead and hit the subscribe button. Like I said, I'm trying to get to 100,000 subscribers. I think that'd be a lot of fun. If you want to learn Bash, go check the description of this video. I have a Bash course. It's completely free. You can go check it out. In fact, if you're watching this video when it just freshly comes out, I'm in the process of uploading each section of the course to my channel. So my channel is being flooded with these videos, which is not great for analytics, but luckily this isn't a business and I don't care if my analytics tank a little bit on this channel because I get to upload for fun on this channel. So that's great. So yeah, thank you everyone for watching. Let me go ahead and quit out of this. We'll quit out all this stuff right here. And yeah, I guess the last thing to say is thank you to my patrons over at Patreon. Thank you so much for your continued support. Oh, wow. Look at this. Let me open this up a little bit so we don't have to scroll. There we go. Wow. Okay. We just barely do have to scroll. Not a big deal. There we go. Perfect. Thank you so much for my patrons over at Patreon. Thank you for your continued support. I love it. You guys are awesome. Look how many there are. This is crazy. Okay. If you want to join my Patreon, there'll be a link to it, of course. I can't promise you anything fun. I can't promise you like behind the scenes video. I don't do anything exclusive. These people just pay me because they want their name at the end of my video. You guys are so awesome. I think that's so amazing. Hopefully I'm delivering on that promise. And yeah, thank you so much for watching. And yeah, here's to when I eventually hit 100,000 subscribers. So yeah, that's all from me. See you guys. And that's how many bytes were sent in a second. So now we have a nice bytes per second thing. So now we have a nice bytes per second metric.